Mm. Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present, and future is the mission of Eco-Environment and Health. Eco-Environment and Health is a journal initiated by prestigious scientists with a strong editorial board, including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design, and broadcasting. The experts will accompany you like a harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision-making that deeply integrates informatics, ecology, and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. The 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a three-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
Hello, Thilo.
Hello, Wei. Good morning or good evening, wherever you are.
Good afternoon to you.
Morning.
I think we have a couple of minutes before we start.
Sure. How are you doing?
I'm doing pretty good. I'm not teaching this semester, so I have a little bit time. Are you teaching this semester?
Yeah, I started teaching in October, but we have it like scheduled and blocked. So my aquatic chemistry is already over. So rest of the semester, I'm free for research.
Okay, that's good. I guess we'll start on time. And Shuming, are you gonna place the record button when we start?
Hi, Dr. Zhang.
Hi. Are you going to record the talk when we start?
Oh yeah, my
Okay.
colleague will do this.
Oh, okay, great.
Okay.
Yeah.
You just let me know when I should share my screen or if you give the introduction, however you prefer.
Yes, I think I will give introduction first, and then I guess Thilo, I think you can share your screen now, and I will. It's 8 o'clock, so I think we should get started. All right, so now it's being recorded, right? I think we
Yeah.
should.
Yeah.
Actually, I just want to confirm. I think we should start.
Okay.
And so it is my great honor to introduce Professor Thilo Hoffmann for today's EEH talk at EEH. And Professor Thilo Hoffmann received his PhD in aquatic geochemistry from Bremen University in 1998. In 2005, Professor Hoffmann became full professor and chair of the Environment Geosciences at the University of Vienna. And he holds that position since then. And he served as a vice dean of the Faculty for Earth Sciences and Geography and Astronomy from 2006 to 2012, then as a dean of the faculty until 2016. He established the University of Vienna Environment Research Network in 2014 and served as its director. This network includes more than 230 scientists from natural sciences, social sciences, humanity, law, and economics. All these disciplines are critical to solve today's environment challenges. So it's amazing work to be able to assemble this diverse team of scientists who are interested in tackle today's grand challenges our societies are facing. And Thilo Hoffmann has a remarkable research record. He published more than 170 peer-reviewed papers, received awards from German Academic Scholarship Foundation, Berlin Technical University, and the German Water Chemistry Society. In 2017, Thilo was appointed a adjunct full professor at Duke University, and in 2018, he was honored as a guest professor at Lancaster University. His group works on nanogeosciences, environmental impact of nanotechnology, trace contaminants, and microplastics, as well as hydrogeology. So with that, I'm going to turn the microphone to Thilo, and he's going to talk about nanotechnology and nanoplastic in plant agriculture.
Thank you very much, Wei, for the very kind introduction. And thanks, of course, also to EEH for the introduction to the seminar. Welcome, good morning or good evening, depending where you are. And in the upcoming 40 minutes, I'd like to guide you about a few ideas about nanotech in plant agriculture. And because it's also popping up pretty often about nanoplastics in plant agriculture. Let's get started maybe with one slide about our university. University of Vienna is pretty old. It's actually the oldest German-speaking university in Europe. It has 96,000 students, so quite big. And out of this, 6,400 scientists. We have 180 studies, 15 faculties, and 5 centers. And the center I founded together with colleagues is actually the youngest about environmental sciences and microbiology. Again, if you think about doing a sabbatical or postdoc or PhD in Vienna, Vienna is a very nice city. It has a lot of quality of living. It's pretty lot of old, nice buildings. That's our office for the ceremonies with beautiful Klimt buildings that are my daughters over here climbing, and here's Greg Lowry from Carnegie Mellon University. So you expect to hike a little bit if you're in Vienna. So it's beautiful, nice. It's a small country, only 8 million people. Yeah, 8 million, that's nothing. So Vienna has 2 million people. So it's a nice and small country, and research is pretty good. So if people are interested in coming to Vienna, just contact me. That's my group. A lot of people working over here. Group is international, and the group is only English speaking. We also only teach in English. So in the master level, there are no German courses anymore. And so it's everything taught in English, which makes it easier to hire internationally. Let's get started. So that's the outline of my talk. I would like to speak in the beginning about the challenge moving from 8 billion people as of last week. HWO said we have 8 billion people to 10 billion people by 2050. And then from there, move to nanotechnology in plant agriculture. And from there, talk a little bit about plastics in agriculture. And some stories here, and then some take-home message. I start right into it because it might be late for you and you want to have your dinner, or you're just coming out of dinner, so I get started right away. Okay, so that's the projection of growth of population on our planet. So 2015, it was 17.5 billion. Now we are already at 8 billion, and prediction is roughly about 10 billion. The most recent scenario says that then it's declining again and population would go down. We will see 2050. This comes, of course, together with a significant increase in food production. So we need way more food by 2050. And estimates say that we need about 60% more food. And this is different for corn, maize, or beans. And so it's really a heavy burden. If you look to food production, which needs to increase, you can also see that this is the production of food at the moment. Yeah, that's what we need. And there's a gap. So we have a production gap, especially in countries with low income. And this is driven a lot also by the consumption of meat. I will talk about this later a little bit. So if you look to the numbers, 2005 to 2050, predicted increase in beef or mutton or pork, poultry, you see massive increase in meat consumption. As of today, about 820 million people have insufficient food, but on the same side, 1/3 of all food is wasted. 2 billion people are deficient in micronutrients, which is pretty important, and food production needs to increase by 60, but maybe of 100%. So food security and food safety is a major challenge of our planet. But food production is already the largest pressure, or think about climate. So 56% of the non-CO2 emissions are stemming from agriculture. So it's really huge production, methane basically. And then about CO2 greenhouse gas emissions, it's about 19 to 29%. So largest non-CO2 greenhouse gas emissions is from agriculture, roughly totaling about 30% of greenhouse gas emissions. And the impact of climate change on yield predictions are negative. So that's the yield, agricultural yield. That's a lot of different models run by Seager. Most predictions show a negative trend. So with climate change, soils becoming more fertile, maybe in the north of Canada or Russia, does not outcompete extending of desert in other parts of the world. So the overall trends on the planet are negative if yield. So we have a problem here. Land use and biodiversity, you know, of course, that we are in times of biodiversity loss. That's really steep. That's also why we call it the Anthropocene. Biodiversity loss is highest ever seen. Yeah. 75% of deforestation is by agriculture, and agriculture already covers 1/3 of our planet. So it is big numbers, big fact. Water, food, energy nexus is central for development. If you look to the total picture of food production, about 30% of the total energy consumption, that's globally, it's 70% for the US, 70% of the global water use, it's 90% by 2050. And then 50% of the nitrogen fertilizers are used by plants, and the rest is lost to groundwater and air. So most of the fertilizers is lost. So we have some problems here too. And this basically is the overall picture from a paper myself and a lot of colleagues were publishing in Nature Food 2 years ago. We just made this picture. That's the burden we have already, yeah, on energy, land use, groundwater, deforestation. But population is increasing and food production needs to increase. And food production basically hits all of the sustainable development goals. There's not a single sustainable development goal which is not basically affected by food production. I normally wouldn't read a text in a talk, but I like this comment from Tamara Lucas and Richard Horton on the EAT Lancet Commission report. And this is pretty heavy stuff. It's like civilization is in crisis. We can no longer feed our population a healthy diet while balancing planetary resources. For the first time in 2,000 years of human history, we are severely out of synchronization with the planet and nature. This crisis is accelerating, stretching Earth to its limits and threatening human and other species' sustained existence. So this report shows a grim outlook to the future, but also solutions. What do we need to do to increase food production? And the Eat Lancet report showed in a nutshell these topics here. First, raise productivity is the single most important step. So we need tech innovation. Link agriculture intensification with natural ecosystem protection. This means we need intensification, not expansion. That's a big topic here in Europe, where we also think about organic growing and less intensification. This will not work globally. So we need intensification, less emissions from fertilizers and plant protection products. Reduce greenhouse gas emissions, spur technology innovation, very important. Manage demand, of course, which means reduce food loss and waste, and shift to healthier diets. So unfortunately, the message is clear: low to moderate meat consumption. We eat too much meat. Yeah, the planet cannot afford the amount of meat we are eating. Nano-enabled plant agriculture I'm talking about is, of course, not the one single solution. That's clear by the problems, but it has great potential and might add to other technologies. So it's an add-on. It might be important. So we are already here in the talk, nanotechnology in plant agriculture, and I would like to show you what's in the market and what will come. So nanotech, most of you, I think, will know it's the new wonder material for about 30 years, many applications, your computer, your mobile phone, electronic devices, solar cells. So nanotech has a lot of applications. So from health to consumer products, daily life, all over is nanotech, food packaging, but also it's coming more in plant agriculture. And this, of course, makes a big difference because it's massive scale. This is a topic which has been debated like 15 to 20 years ago, much in gray literature. So if you look here, there's a lot of report, a lot of gray literature, and it is claimed that it has the potential to revolutionize agriculture. But we have not seen it so far. So what's the problem? So we have a controversial discussion on risks linked to nanoculture, and I would like to dig a little bit deeper today in nanotech in agriculture. What is the principle? The principle often is that you have a selective nanocarrier, and this nanocarrier delivers a cargo at demand. The at demand is very important. So that's your carrier here. Yeah, it's like your rocket. Might be silica, might be carbon nanotube, might be gold, a quantum dot, a magnetic nanoparticle. And then you charge it with a cargo like a pesticide or a fertilizer or DNA, a protein or an activator. And then you, for example, have a release of fertilizer on demand. Yeah, the idea is it doesn't go to the groundwater, or you deliver micronutrients. Or it delivers target-specific a pesticide, or, for example, DNA to a chloroplast. Or you can do in vivo labeling and imaging. And for example, that's an example from the Strano lab at MIT, where you see that chitosan coated single-walled carbon nanotubes deliver the cargo, the RNA, inside the chloroplast. So the technique works. It's interesting. So you get it on the cell, it passes the lipid membrane, it enters the chloroplast, and finally it is delivered inside the chloroplast itself. So it really works nicely and has a lot of potential. What do you see on the market? Also is nanoplant protection products. So for example, Asteroid FC from Wivecop or DuPont Coeseed or other products. So some products are on the market, but don't get offended, but they're not so smart at the moment. So this release, when you need it, the targeted release, we are not there. We would need to have the release exactly at the time point where needed, where a sensor detects the pest. So there's a lot of research to do, but there are also interesting applications. Fertilizers and nutrients, I tell you first why this is so important. You, of course, know that 50% of all nitrogen is lost. You might also know that over 90% of the phosphorus, which is mined globally, is going to agriculture. So both nitrogen and phosphorus, they are planetary boundaries, yeah? And this is by agriculture. If you look to Earth history, if you look to anoxia in oceans, this was always linked to high phosphorus inputs. So most of the phosphorus and nitrogen is going to the ocean. So of course, if you could change this, if you could make the use of nitrogen more efficient, yeah, more than 50% is lost to the atmosphere with laughing gas or to the groundwater as nitrate. If you can make this more efficient, this would help a lot. But also micronutrients. Micronutrients are of major importance, and I talk about this a little bit later. Nanosensors and chips, that's cool in a way, yeah. So not much risk here. So for example, plant status or enzymes, soil growth conditions, pathogens, contaminants, identification. So what you have an analyte, let's say drought or a contaminant or the plant status. You have a bioreceptor, an enzyme, an antibody. You have your nanoparticle, yeah? Then you have the transducer, electrochemical or optical or mass, and then you have a signal. So for example, this is here from Michigan, from 2 examples from the Day Lab as MSU here, or Biosensor Lab, also MSU, for example, where you can detect with a magnetic iron nanoparticle E. coli, yeah? And the idea would be that then in spinach, you can find E. coli. This is heavily important, I think. It's 120 billion per year in the US health costs for this illnesses. Or you can detect listeria basically with a magnetic antibody, which is here at the nanoparticle, and then you have lateral flow analysis and can detect listeria. So a lot of applications or plant diseases. So nanosensors and chips, I talk later where we see the perspective for this. So we wrote a perspective paper, yeah, and if you don't have access to Nature Food, I share the tiny URL over here. You just need to remember this last numbers here, or write me an email and I can send you the document. And so we published a paper about technology readiness and overcoming barriers to sustainably implement nanotech-enabled plant agriculture. So this is an expert judgment. So you can criticize this. We just did our judgment, what we think. What do we have here on the y-axis? On the y-axis, we have the technology performance level. We said that here there's no or moderate improvement. Here we have significant improvement, and that's a game changer. So that's the technology performance level. And this level here, the x-axis, is the tech readiness level. So we said, okay, proof of concept, lab testing, field trials, validation. So let's look at points where, and we might be wrong, it's just an expert guess of all these people here involved. Yeah, we just said that soil conditioning, we have trials, but what we see is not so promising. On contrast, if you look to nano carrier bound gene editing, this is probably a game changer and heavily investigated. Also because regulation is very different. If you look to the US and to my understanding also in China, because this is not changing the DNA to the next generation, this would not be considered GMO food in the US and in China. In Europe, it still would be considered GMO food. So this is a big difference, but you can really introduce new traits in a plant, which might be very important. More advanced is nanocarrier bound RNA interference. Since Corona, everybody knows what RNA is. So RNA interference is a very important plant protection mechanism. And this is going ahead. So this is getting very interesting. And I would also say nanocarrier bound micronutrients might be important. If you ask me 2 years later, I would maybe scale this down a little bit and would scale up the micronutrients. So the research of the last 2 years on micronutrients show that they really have a good and big potential to increase yield or defeat pests. And then nanoactives and nanopesticides, they are on the market and they might change things really. The overall opportunities for nanotech and plant agriculture, plant protection. So what you need for plant protection, this is the pesticides, actives, and growth enhancer, you need smart delivery, smart release. Yeah, slow is not enough. This has been debated over a long time. So it's not essentially enough to just say my pesticide is released slower. This is done by PE coatings or something. You need a higher efficacy. You need to reduce the loss. You really have to turn this knob to make it 20% more efficient, and then it's worth. Nanofertilizer is getting interesting. It's changing here. Deliver where, when, and what is needed. Reduce loss. Much work has been done on micronutrients in the last 2 years to suppress diseases or increase stress tolerance, stimulate photosynthesis. There are very good papers, many options: nano copper oxides, copper phosphorus, copper sulfides, molybdenum, and zinc and cerium, or biopolymers for nutrient delivery. So I would say this work here has even increased in the last 2 years. Sorry. Sensors, smart. I think probably best at high value crops. There's less concern because you don't eat them later. So sensors could be very interesting. And genetic engineering, of course, has the highest potential, but highest concern, and regulations differ. So nanocarrier facilitated delivery of genome editing, for example, when you have transient and controlled Cas9 expression without incorporation of foreign DNA. That's the point. You don't have the incorporation of the foreign DNA. And for regulation, this means that this might not be GMO food. Or you have topical application of nanostabilized double-stranded RNA to induce RNA interference as plant protection mechanism. So that's also a thing which is heavily investigated recently. How to overcome barriers. We also discussed how we can move forward. Details are here in the paper. Precision spraying makes sense. Aerosol mediated applications, leaf dipping, this is done. Targeted delivery, smart material selection. Don't start with something which is toxic from the beginning. Controlled exposure. You need sentiment science, and of course you need a lot of involvement and discussion with consumers. I come back to this in a summary, because there's of course also the risk of nanotech in agriculture. And the risk using nanotech in agriculture, it's large scale. You talk about 1/3 of planet Earth. And this needs to be evaluated very critical. So the perspective of the consumer and differing regional and global perspectives needs to be taken into account. What I like to say is that what works, for example, in Europe or China does not necessarily need to work in the US or South America. So you need the discussion with the consumers and with the producers. And of course, there are a lot of questions on risks, on exposition and hazard. My recommendation would be start here on the hazard side, that the hazard is low of the materials you use. So this would be the most important thing. And then questions like what is impact on nutrient quality, transgenerational study, trophic transfer studies, chronic low dose exposure data, or effects on the rhizosphere and biota. So that's quite important. Jason White is doing a lot of work over here from Connecticut Agricultural Research Station. On the other side, my group, we worked for 15 years in risk assessment of engineered nanoparticles. So there are, I would say, 20 years of environmental risk assessment for engineered nanoparticles. And we gathered a lot of knowledge. There are 10,000 plus publications on risk assessment for nano. So we do not need to start from the beginning. Much will be transferable to nano-enabled agriculture. There are a lot of monitoring. This is from Klaus Svensson here from the UK, a project we have been involved in, where you combine basically the emissions from productions, from shipping in the consumer, and then how does this move in the air, in soil and water, and what is the risk in which pictures. And you can do the same principle for nano ag. So there is a lot of research there. You don't need to start from the beginning. There are thousands, 10,000s of publications. I summarize the lessons learned from 20 years risk assessment of nanotechnology in consumer products. And there's a developing consensus that ENP may pose a low environmental risk. So high risk are not expected, but because, no scientist is without but because of uncertainty and lack of data in many areas, definite conclusions cannot be drawn. Well, ask a scientist about definite conclusions, you never get this because they are not there. Question is, can this be transformed to nano-enabled agriculture? I would say in most cases, yes. There are questions on the right data for a holistic One Health approach, chronic low dose exposure. trophic transfer, transgenerational studies, containment of exposure. I mean, in vitro exposure and tox testing might help a lot, but this has to be done. And then translation of incomplete understood science into regulation and policy is challenging. We know this with the corona crisis now for 3 years. Scientists never completely understand things. This is impossible. Yeah, but then getting this into regulation, you see how difficult this was and is with corona. It's heavy. So there's a lot of political work needed. And integration of technology innovation and risk assessment is needed to ensure that the benefits of the technology are gained with the minimization of possible effects. I mean, that's clear. So I would say innovation and precaution are equally important, absolutely. My personal message would be also only go nano if nano is needed. If you don't need nano, yeah, it is expensive. You need a lot of energy, yeah. You have to do the risk assessment. So ask yourself in the beginning, is nano needed? So ask the question, is my effect nano-specific? So only go nano if it is needed. It doesn't make sense just to go nano because it's a beautiful word, it sounds better. Just do it when the nano effect is there and is the driver. In case of agriculture, covering 1/3 of Earth's terrestrial surface, you need to do it right. So you need to be careful with this. From here, I would like to go to the last part of the talk. We have roughly about 10 minutes and this will work out. So it's not directly connected, but it's indirectly connected. And I will show this in a minute because questions are the same in agriculture. I will specifically talk about contaminant transport with plastics. So you have seen this slide before, yeah? Agriculture in the Anthropocene. And now I just added myself and plastics. Raise productivity is the single most important step. I just read this sentence 20 minutes ago. And of course, plastics play an important role because productivity, if you think of greenhouses, if you think of mulching films, extending the growth season, yeah, mulching films, plastics are used heavily in Europe, in China, in the US, all over. And then the second sentence I was reading, link agricultural intensification with natural ecosystem protection, yada, 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 less emissions. Well, plastics help a lot with intensification. And they help, of course, lower the emissions because you need less fertilizers, less plant protection products, you need less water, you have less greenhouse gas emissions. Spur technology innovation, I will tell you later, this is heavily needed for plastics, and then manage demand, reduce food loss. Yeah, food loss, packaging and plastic is important. So my message is that plastics play an important present and also future role in plant agriculture. You probably know the UNEA 5.2 treaty, which means that in the next 2 years, we want to find solutions globally on plastics. So this is heavy negotiations and heavy pressures going on. And there's, of course, a lot of discussion if plastics should be out of agriculture. My personal viewpoint is this will not be the case. We need it for irrigation, we need it for climate change, for extending the growth season, but a lot is going wrong with plastics in agriculture right now. Where's plastics used? So just have a look here. So for example, you have polymer-coated fertilizer with PE or LDPE or cellulose. Yeah. Cellulose might not so be problematic, but if you have PE, polyethylene is not degraded, end of story. Yeah, you cannot degrade PE. This is not happening. So these PE coatings will stay in soil. You have fertilizer sacks or bulk containers, seedling plug trays, nursery checks. And then here in red, mulching films. Mulching films dominate the plastic market. You have LDPE, but you also have polyvinyl chloride, yeah, which always contains phthalates. So, and they can normally not be recovered and they can never be recycled at the moment. And so often this is tilled into the soil and changes the soil physical properties. But once again, we have the same problem like in the beginning of the talk. We need to increase food production. So you cannot easily say, okay, just get rid of the plastics. We have 20% less food production. At the same moment, we need to increase food production. So we really have a wicked problem over here. Textile, greenhouses, you know, shade and protective nets, irrigation trips, of course, irrigation pipes, support tiles, maybe not so much, some sacks, storage crates, but also like pesticide containers. To give you some numbers, intentional inputs, it's about 12.5 million tons per year. And this is heavily increasing. That's data from last year FAO report. 50% of the market, 40 to 50% of films, yeah, that's for most countries. Soil is the dominant receptor, and crops, it's not fishery and forestry, it's crops, it's the largest user. And lifetime for some users is very short. If you think about multifilms, yeah, the overall lifetime is everything less than a year. In addition, you have unintentional inputs with biosolids, tire wear, for example. I talk about this at the end of the talk, wind and recycled wastewater. So here we go. I will address today only are micro and nanoplastics a vector for contaminant transport. I do so because this is very often debated, and I give you the answer right away, no. But as a scientist, I say but. So what is the story? The story is that, for example, you have a wastewater treatment plant here. Also, you have, of course, tire wear coming from the road runoff. And then you have the biosolids with tire wear particles. And then the tire wear particles here with your biosolids might go to the field. Or you have mulching films, they degrade, and then there are plastics. Or you have your agrochemicals, the agrochemicals might adsorb to the plastics. And then these contaminants here might travel with the plastics down to the groundwater. And that's something which you read very often in papers, for example, that you say, okay, plastics, especially nanoplastics, might, due to the large surface area, enhance contaminant transport in soil. And we published this paper in Nature Earth Communication. Nature Communication, Earth and Environment, I think beginning this year. And you have two processes which you can separate. The first process is your system is in equilibrium, which means your contaminant, which is linked to the plastic here, desorbs. The smaller the particle, the faster. And then finally, it is desorbed and adsorbed to the soil. Or you have a fast transport, decoupled. And then the contaminant is here inside, but the transport is so fast that it still stays on your plastic. Case number A, if you reach equilibrium, your contaminant is lost, it's going to soil. So finally, the plastics will not play a role. Case number B here, your microplastic will add to the contaminant transport. This picture here is a little bit busy, and because it's late, I don't run you over it completely. Let's just focus on these two here. Just focus on this here. So the one thing is go to dinner, it doesn't matter. And the one thing here, it is relevant. So that's the first situation. You have your contaminant loading on your nanoparticle. Yeah, that's the contaminant on your nanoparticle. And then just while travel time, it desorbs out of your plastic. And because simply you have so much more soil and so much more water than plastic, the equilibrium partitioning will go on the side of the soil. So finally, the plastics will not transport any more contaminants. Yeah. Or the other situations, this is a pretty fast transport. Yeah, soil could happen. And then the contaminant sticks to the plastic, and then it will transport your contaminant. It will not go to the soil. And of course, from 101 civil engineering, you know that this is nothing else than the Darmköhler number. So the co-transport depends on the particle size, distribution coefficient, residence time. So it is the transport versus the desorption timescale. So you can just calculate what is faster. Is desorption faster? Then it's equilibrium, or is transport faster? Then it's decoupled. And that's the Darmköhler number. And you can say Darmköhler numbers smaller 1, then it is relevant, it's decoupled, or Darmköhler number larger than 100, it's not relevant. And we published a paper for engineered nanoparticles. I think this was 7-8 years ago. Nice cited. And I felt we have to do this again for plastics. We did, of course, completely different calculations. That's the summary. I run you over this slide because it's not easy to read. So what we did is we checked, this is your plastic particle here. Okay, that's the plastic particle. And then we checked, do you have intra-particle diffusion? Is your contaminant diffusing out here? And is this the rate limiting step? Yeah. just say you have a PEH or a PCB or a pesticide inside your plastic, and it wants to diffuse out. This could be the rate limiting step. And then this is the equation for diffusion. So you need the apparent diffusion coefficient, you need the radius, you need the tortuosity, and you need the radius goes, of course, into the equation r squared. Yeah. Or that's the other possibility, is it aqueous boundary layer diffusion. Every particle has an aqueous boundary layer around it. So the rate limiting step for the kinetics could also be the aqueous boundary layer diffusion over here. So then it would be this equation here. Don't get tricked that this only depends on the radius, because in this parameter here, for the thickness, the radius is in again. So again, also this depends on r squared. Take home message to make it very simple. We calculated interparticle diffusion for particles 1 micrometer and for particles 100 micrometer. And you see that for all combinations we had of polyethylene, polystyrene, PVC, PDMS, or tire materials, and all contaminants we found in the literature, we found that simply forget it. You never reach decoupled conditions. You're always at equilibrium, which means you can go to dinner, it's not relevant. If the rate limiting step would be aqueous boundary layer diffusion, then for a few sets of contaminants, like here PCBs, but that's not the most typical thing on agricultural soils, you see, yes, PCBs matter. Okay, here for polyethylene, we have the most data for polyethylene until 1 micrometer. But if you go to smaller particles like nanoplastics, again, forget it. They will not play a role. So the story is very short. Nanoplastics don't play a role for contaminant transport in soil. It's just like, it's not possible. The but. So the but is what might happen, and it's just the few last slide, what might happen if there is no co-transport? It means that your contaminant leaches out to the soil. They leach, very simple. And that's the experiments we were just doing recently, and I just checked half an hour ago if the paper is accepted. We submitted the paper to ES&T. Reviews came back. Reviews are very positive. We answered all the questions, resubmitted it a week ago. So honestly, I'm expecting every day to get the paper through. So because we could answer all questions from the reviewers. So paper will come out this week, hopefully, and I can send you the link if you like to. So what we did, we used tire wear additives because tire wear is massively brought with biosolids or wind to agricultural fields. And we looked to tire wear additives. If the tire wear additives are taken up to the leaf, to the edible part of the leaf, and this has been lettuce. So that's the experiment. We look to these tire additives. If you're working with plastics and tire additives, you know that they're of much concern. Diphenylguanidine, bitranthocin, HMMM, 6-PPD, and especially the 6-PPD quinone, which is known to be toxic. And there was the science paper last year about Soho salmon in the US, about an Arctic, about 6-PPD quinone, pretty toxic. So we analyzed these additives here from tire wear and looked what happened. So what do you see over here? Left side. Left side is the translocation factor. It means what ends up in the leaves and what is in the roots. And what you see is that HMMM, this compound, I go back one slide, this compound here, which looks very strange, it has a sweet spot in the partitioning coefficient to pass the root epithelium, and it ends up in the leaf. So the translocation factor of 10 means that you have 10 times more in the leaf than in the root. Opposite, the 6-PPD quinone, it's very hydrophilic. It doesn't pass the membrane, so it stays basically in the root. And then here on the right side, you have it exactly the other way around. That's the root concentration factor. I'm sorry that the colors have been changed. The colors, a PhD student arranged it always like that, the lightest colors on the top. Here you see that in the root, 6-PPD quinone, this has the highest concentration in the root. So it stays in the root, but it also goes up to the leaf a little bit. For DPG, I can show you a typical picture. I could show it for all, but then the talk is too long. So you see a concentration in the leaf going up, that's leaf concentration, and then it's going down, which is metabolism in the plant. So it's metabolized because the plant wants to get rid of it. So this is for the spike dosing. So if you have a spike dosing here, it goes up, but then it goes down again. So we did a second experiment, different uptake pattern, spike versus the constant dosing. So what we did here is we now put the tire wear particle into the hydroponic experiment. So it constantly leached out. So it was not a spike dosing, it constantly leached out of the tire wear. And what you can see then is in the leaf that DPG goes up, but also the quinone, the 6-PPD quinone and the 6-PPD, they end up in the leaf at a lower concentration, but they end up, same for the HMMM. So all substances basically end up in the edible part of the plant. And that's of course concerning. So take home message, I'm pretty good in time. So take home messages from my talk today is agriculture will need to intensify it. Nanotechnology and plastic both will play an important role in the future and help to reduce food waste, energy, water, fertilizer, and pesticide use. The number of papers on nanoparticles in plant agriculture is growing, but we haven't seen the breakthrough so far. Still, I see huge potential. I think in a few years we are there, especially micronutrients. I think it's hot. Risk needs to be evaluated very carefully. First, large-scale intentional use of nanoparticles. Yeah, it's 1/3 of planet Earth, but there's much transferable knowledge from over 20 years of nano environmental risk assessment. Nanoplastics, I want to make this statement here, are not an important vector for co-transport of chemicals. Forget about this to deeper soil layers and groundwater. But the but is additives are of concern. They will increase the total flux of xenobiotics to environmental systems and might meet you later at the dinner plate. Yeah, innovation needed. Innovation is we need better additives. Less toxic additives, non-toxic additives, and biodegradable additives. And then also innovation is needed for non-retrievable plastics. They are of concern, mulching films. It is simply too much, 6 million tons, to just till them into the soil. Yeah, this doesn't work. So the solution here is recycling, yeah, retrieve it from the field, or recycling, or biodegradable. So much research is needed on biodegradable plastics. With this, I would like to thank you very much for listening, and I'm very happy to take questions.
Thanks so much, Thilo. That's a fantastic presentation. It was actually great to see some of your recent work since last time you gave a talk in our university. That presentation was also well received, and it's really mind-boggling to think about like the great challenge we have, especially with the food production and with the amount of population we have on this planet. As you show, in many cases we are kind of stretching, exceed the planetary boundaries, and so that's really a daunting challenges for us. And you kind of show that the nanotechnology could be one of the solutions, and there's many applications. Of course, we need to consider its risk. It seems that we need we need the participation engagement from a lot of different stakeholders like farmers and government agencies and industry and so on. And I was actually particularly kind of intrigued by the calculations on the effect of a co-transport by micro and nanoplastic. I think you showed last time for the nanoparticles, but this time I think it's kind of a highlights again that we really need to understand the physics when we kind of think about the problem we have. So I believe that there are going to be a lot of questions from the audience. So I will first open a microphone to the audience, and I guess the other people are gonna monitor the question from other streaming platforms. But I'm going to also look at the chat box in the Zoom. So for the participants, if you have any questions, you can ask us to unmute yourself and you can speak, or you can type your question in the chat box.
Yeah, thanks, Wei. I also fully agree with you. The challenges ahead are significant. And coming from a European perspective, I grew up in Germany, a little bit bigger country than Austria. Austria has 8 million, Germany has 80 million people. But you know that Germany has a very strong environmental movement and a very strong green movement. And I appreciate this. And you know that Germany moved out of atomic power plants. At the moment, we have this heavy energy crisis, but still, even with the energy crisis, because there's no more gas from Russia, Germany is moving out of atomic power plants within the next 5 months. And this is very interesting because there is no other source than fossil sources. Mm-hmm. I say this because I'm an environmentalist. Yeah, I really try to think, what can we do better for the planet? But it's not as easy, from my perspective, as to say, okay, just say no plastic. We ban plastic. We ban plastic straws, or we ban plastic completely in agriculture. I see these claims, but to my perspective, this is too simple, because then you need immediately way more water, or in some parts of the world, you cannot grow without plastic. So, and for me, as someone who wants to protect the environment, sometimes it's really hard to say that you need plastic. Yeah, it's better. Or we have the discussion about plastic bottles and bottled drinking water. So, for example, you see in Vienna in a supermarket, if you come here, traditionally, I mean, like in the last 10 years, a yogurt would be in a PE plastic. Yeah. Mm-hmm. Relatively easy to recycle PE. You have the aluminum foil. This can go to waste collection, and waste collection is super high in Austria. And the PE can be cleaned, and it goes to PE collection. And now it is replaced in the supermarket shelf more to glass. And you see a glass with a happy cow and the happy farmer, and sold as environmental friendly and shipped 500 kilometers from Innsbruck here to Vienna. Mm-hmm. It consumes so much more fuel. So I think it's a wicked problem. There are no so easy answers. Yeah. So I'm
right.
I'm curious about questions. So I'm reading the questions here. Or do you want to read them?
Well, and if you can look at the chat box, that's fine.
So one question was, and please, if you have any questions, just bug me. Just ask. All questions are welcome. So the first comment from the chat was, thank you very much for the talk. I have one question. If micro nanoplastics were not vectors for transport chemicals in soil or groundwater, what about in water environments? Very good question. I would say there are, of course, nanoplastics and microplastics in groundwater. I started with groundwater. Yeah. There is no spot on planet Earth where you don't have plastics, because it's transported with air. Yeah, it's same like PFAS. It's transported with air. So you will have seen in the last 2 years Nature papers, maybe a little bit too late now, that you find plastics in Arctic, or you find it on the Mount Everest or in tea bags. But that's clear. We produce it like hell, 380 or 400 million tons. So it must be everywhere. You find it in human liver, you find it in the lung, you find it all over. But in groundwater, I mean, groundwater is well investigated for decades, and groundwater is a very good filter. It's an excellent filter. And there have been many studies on transport of colloids in groundwater, and they stem from the radioactive test sites. So if you look to the US, to white sand test sites, Nevada test sites, from the early subsurface atomic bomb tests, there were a lot of investigations about radionuclide transport in the subsurface, McCarthy, Sahara in the 80s, for example. And you see that in groundwater, yes, colloids travel, clay colloids travel, radionuclides can be absorbed, and they can travel over larger distances than you expect. But if you think mass-wise, does this matter for organic contaminants? My very honest answer is no, forget it. It does not play a role. In groundwater, persistent, mobile, toxic contaminants play a role. or very persistent, very mobile contaminants play a role. Like, for example, PFAS contamination of groundwater, that's a big issue, or pesticides, or melamine, or others. Yeah. So I would say that's a topic where just by the calculations I have shown you, you can calculate this. Yeah. I would say that's not a research topic where you can gain a lot. So groundwater, forget it. Let's go to surface water. Surface water, of course, you have a lot of organics, yeah, natural organic matter, natural flux. We just published a paper on flux in river water and water research, and this dominates the system. So once again, you don't have so much plastic that it matters for co-transport. So I would say the co-transport is not the effect which is interesting, to my opinion. But why it matters is that plastic contains additives. If you look to tire wear, 50%, this is an overlooked number, 50% of the total microplastics is tire wear particles. And tire wear consists of a lot of additives, yeah, hundreds. Many are even not known to the public or researchers because they're classified by the companies. Yeah. And then, of course, tire wear ends up in rivers, or it ends up on soils, and these additives leach. Or same for PVC. PVC contain 30 to 60% phthalate. So if you look to a sediment, the phthalate burden of a sediment might come from PVC plastics. So the question is, plastics play a role for the transport of additives to the environment, for the flux of the additives, but not for co-transport. So co-transport, I would say, that's not the process which matters, but the flux of the contaminants, total flux, yeah, this matters because these additives are linked to the plastics. Let me run through the questions. The next one, very interesting paper on Science, the global threat for plastic pollution. Yeah, thanks. I will read it and check this paper out. I check it in a minute if I've seen it before. Thank you for the talk. I do have one question. That soil is quite a complex system. That's true. When you use nano products such as nano fertilizer in a place for a plant that might work, but another bee place for bee plant, that efficiency might greatly change. So how can we say our product is a success? Excellent question. Yeah. By the way, also excellent for plastics. I come to this in a second. You have seen in my talk, it wasn't pretty fast, that for microbiome or soil manipulation, I said that the tech level is very low. Exactly for this reason. You have a lot of soil. It is almost impossible to deliver it directly to the plant. What studies show is that for micronutrients at very low concentrations, they can make a release and uptake more efficient. And this seems to work. For phosphorus and nitrogen, but I might be wrong, I haven't scanned the literature in the last weeks, I haven't seen for this massive products that it works because the conditions are very different in various soils. But everything which you apply to the soil, which you spray to the soil, I'm skeptical because it's a lot of soil and nano needs a lot of energy to produce it. So the question is this ever feasible? Very different if you make precision spraying or leaf dipping or seed coating, which is done, there it works way better. So I would like to answer your question that try to avoid the soil. Sorry for the soil scientists, but it's too complex. Try to get it directly to the plant, to your target. And this is, of course, also important for plastics. If you look to plastics biodegradation, there's a lot of confusion. You see papers with PE degradation. PE doesn't degrade, yeah, end of story. But if you look to PBAT or if you look to other polymers which degrade in soil, and they're the first long-term studies, you see that in some soils, biodegradable plastics degrade very good. And then you bring the same plastic to another soil with a lower pH value, yeah, and then you break the acetate bonds and this produces acid, yeah. The same plastic doesn't degrade. In 3 years, only 20%. So also for plastics, soil plays a major role. So you're absolutely right. Good question. Not easy.
So I have a comment here. I guess probably pick up from the last comments you said about biodegradable plastics. A few years ago, when I was working on a proposal, I learned that basically the definition of a biodegradation for plastics is based on the degradation in composting processes. So I think that raises a big question. Even if some plastic are degradable in composting, whether that's gonna still be degradable in soil conditions. I don't know whether that has changed, like the standards, a definition of biodegradability changed or not, but as that seems a big technical challenge that we need to think about. The other comments I have is actually on the plastic. I think I like your idea about the plastic are not for coal transport. I think we also need to think about in big picture, like plastic is a part of a carbon cycle, and a significant percentage of fossil fuel we extracted is used to produce plastics, and then we don't know how those plastics moves through our environment. So I think the paper I mentioned, published in Science last year, was talking about irreversible plastic pollution. So all the plastic ends up in the ocean, and eventually they're going to settle down to the ocean bottom. But still, it takes a very, very long time. So there's still a lot of plastic suspended in the water columns throughout the ocean. So I think it's really a big challenge in terms of the plastic pollution.
Absolutely. So the science paper I opened it is by Matthew McLeod, a very good friend, and Hans-Peter Arp. We're working together with him, and Annika Jenecke from UFZ. So very good friends. Absolutely correct. And this is basically the statement in my final summary slide, which I made at the bottom. For additives, we need innovation. Yeah. Mm-hmm. But for the rest of the plastics, the clear message, I would fully agree. It's not a solution at 10 million tons a year to just till it into the soil. Yeah, it stays there forever. I mean, 50, 100, 500 years, and we are accumulating basically these plastics, which might hit soil fertility and yield. And biodegradable plastics, we need technology innovation. We are not there. It's a good thing. So for things we cannot retrieve, then we should think really about biodegradables. And then, of course, it would be better way from my perspective if we start like bio-based. So that's also a confusion, which is very often. So plastics are from fossil resources or bio-based. Bio-based is the lower fraction. And then they can be biodegradable or not, both of them. Yeah. So fossil can be biodegradable, or bio-based can be biodegradable, or bio-based can be non-biodegradable. So the best thing would be bio-based biodegradable plastics to use here. So I would fully agree with Matthews. I see it exactly this way, like in the science paper, that we need to act. I just came back last year from a conference organized by myself and others from EEH Zurich. It was in Switzerland, Monte Verita. It's like a Gordon conference about microplastics. Yeah. And there was a lot of research, and there was often there was the song, "We do not know, we need more research." And I'm a scientist. Of course, I also say myself, we do not know, we need more research. But then at the end, I was really like, honestly, guys, we know so much. There's so much polymer research. There's so much nano research. It is time to act. We don't need to wait. It's not a smart idea to basically pollute the oceans, the rivers, and soil with plastics, which doesn't degrade. Full stop. So we can think about solutions now. Mm-hmm. Research is good, but we don't need research for the next 20 years.
Great. Thilo, there's a question in the Q&A session. It's from Chen Jun. It says, "Hi, Thilo, brilliant work, talk. I have a question to the paper you just accepted in ES&T. How do you determine if chemicals were attached onto the surface of the roots instead of inside the root tissue? when calculating the leaf-root ratio and the bioconcentration factor?
Yeah, perfect. You hit it exactly. We don't know exactly where it is. So what we couldn't do so far, we couldn't track precisely, is it the outside of the root? Is it inside in the xylem? Is it moving up? So what we did at the end basically is, of course, we slaughtered all the experiments. We took the plant, we dissected the roots basically, and then the leaves. And then very simply, we just compared total concentrations per mass in the roots, in the complete root, and in the leaf. But we couldn't tell you, is it on the outside? Was it like by hydrophobicity or too hydrophilic that it sticks outside or inside the membrane, or in the leaf? Though we couldn't say so. What we saw is, which is interesting, that they get metabolized and especially conjugated. So you can degrade it, or a detox mechanism too is conjugation. And especially with HMMM, and we saw, which is this fancy molecule, we saw it gets conjugated with sugars. So you see in the MS scans, we did this accordingly to the proof of evidence, what you can do with MS. We saw that we get a lot of conjugates with sugars for the plants to detox. Yeah, but yeah, good question. This is steps we want to do further. Where is it exactly, and what happens, and what is the transporter? So this have been, I wouldn't say preliminary experiments, but it is a proof of concept, and now we continue the same experiments in soils.
Great. There's another question from another platform. So the question is there a good side of nanoplastic for plants? How do the disadvantages outweigh the advantages? So basically, whether there's benefits of a nanoplastic to plants.
Interesting questions. I never thought about this. I mean, what I answered clearly is that there's a lot of benefits of plastics in plant agriculture. That's clear. That's not the question. Maybe a second point is, because there's much ado about nanoplastics, I'm surprised, I have to say, because it's clear that macroplastics degrade to microplastics, and of course microplastics degrade to nanoplastics, and then at the end, depending what type they are, they get fully mineralized after half a year or 500 years. Yeah. So you have a continuum from macro to micro to nano. Is there a benefit from nano? I don't know. Maybe some bugs can eat them and produce energy out of them. I have to think about that. Honestly, I don't know.
That's great. Are there other questions from the audience? From other streaming platforms? All right. Okay, so this is great. This is an exciting discussion, Thilo. And I also want to say, I fully agree with you about sensors, like nano sensors. I think that's one of the bright spots in the future, to think about how we can develop sensors to monitor the soils, the plants, and the water environments. And I think the nanotechnology has a great potential there.
Absolutely, yeah. And there you don't have the big risk question, because you don't have an emission large scale. Yeah, I would fully agree.
All right. Thanks so much, Thilo. This is a great talk, and I really enjoyed the question and answer session. And thanks so much for your talk at EEH.
Thank you for inviting me. It was a pleasure to talk to all of you, and thanks to stay up so long or so early. So yeah, thanks from my side from Vienna. It was a great pleasure.
All right. Bye.
Bye. Thank you so much, Wei. Bye. Hope to see you soon.